case some of you don't know, I'm a tutor down in the Learning Center. So you guys have taken one of her exams already, so you might know what to expect for this one, right? So there's gonna be multiple choice, and then there's gonna be some short answers. This review is different than her review on Canvas. So I would recommend also printing that out and going through that at least once before your exam next week. So we have 7 problems that we're gonna do here today, right? So we're gonna start it off with talking about the difference between discrete and continuous. So what does discrete mean?
Like one whole thing.
Right. And continuous?
Everything going.
Yeah, right. It can be any amount of fraction or decimal between 2 whole numbers, right? So if we need to figure out if this data is going to be discrete or continuous, the number of customers who shopped at the grocery store today, what's that going to be?
Discrete.
Discrete, right? Because you can't have half of a customer. So those are all going to be full whole numbers there. How about miles driven on your weekend road trip? Why is that continuous?
Because a mile can be like so many, like 1.1 miles.
Right. Right, because we can have a fraction of a mile. Time spent waiting in line.
Continuous.
Continuous. Because you can spend seconds, milliseconds, right? That can keep going further and further down. Phone calls made to customer service last month. Discrete. So, why do we need to know whether something is discrete data or continuous data? Formulas, right? So, when you look on your formula sheet, it has discrete probability distributions, and then it has binomial and Poisson. So, if it's discrete probability, we know we need to be looking at that first one. So, any questions on discrete versus continuous? Okay, let's talk about number 2. So we have a sign-in sheet and a review right up here. So number 2, we have 2 parts of this. We need to first figure out, is the problem binomial or Poisson, and then we need to solve what they're asking for. So, for part A, what is the probability that at least 5 of the 12 flights today arrive on time? Past data shows that flights arrive on time 60% of the time. So is that going to be binomial or Poisson?
Binomial.
Why binomial?
Because either you arrive on time or you don't.
Right. It's a yes or no situation. So whenever it's yes or no, that tells us it's binomial. So we can look on our formula sheet, right? So we're looking under the binomial distribution now. So we have a formula for binomial distribution. We need to know N, P, and X. What does N stand for?
Sample size.
Sample size. What's our sample size here?
12.
Okay. What does P stand for?
Probability.
Probability, proportion, right? So what's our P here?
60.
0.6. What about X?
So how many times?
So we're looking at least 5. So you'll run into problems where it's at least 5, at most 5, no more than 5. So at least 5, if we look at a number line here, does at least 5 include 5? Yes? And is it gonna be 5 and greater, or 5 and less?
5 or greater.
5 and greater, right? Because at the very least, we want to have 5. So, if we want to know the probability of at least 5 flights arriving on time, what should we do?
You gotta look at the table.
The table, right? Because otherwise, there's what, 12 flights in a day? We would have to do the formula for 5 through 12. You're not gonna have time to do that on the exam, right? So we have a table. We have 2 different tables for binomial problems, right? We have individual and we have cumulative. Which one are we looking at?
Cumulative.
Cumulative, and why? Okay, so when we're looking at cumulative, what will we be looking at?
You wanna do the 4, 1 minus 4, right? 4 and less.
Right, so what's up along the top of your cumulative binomial?
So the probabilities, is that what you're?
So the probabilities are up along the top, right?
Yeah.
So we need to find where the probability is 0.6. And then over on the left-hand side, you have n's and x's, right? So our n is 12. Our p is 0.6. And we want to look for the probability of here at 4. Because we want to take 1 minus whatever that number is in order to give us 5 and greater. Any questions on that?
Can you explain again why we use the cumulative and not the individual table?
So individual will just give us what's the
Oh.
probability of exactly 1,
Okay.
exactly 2. So we could look up in the individual table 5, 6, 7, 8, all the way through 12 and add up each of those. But if she gives you a situation where she wants to know probability of at least 5 of the 2,000 flights today arriving on time, that's a lot of adding up to do, right? So we look up at the cumulative table at 4, which is 0 through 4 added up, all of their probabilities. And then we can just subtract 1 from that, and that gives us the other side. So when we look up the probability in our cumulative table at 4, what do we get?
0.0573.
0.0573. So what would the answer be to what's the probability that at least 5 of the 12 flights arrive on time? 0.9427, right? All we're doing is 1 minus this 0.0573. So how do you guys feel about that one? Any questions? Yes?
Wait, so it's under 4.6, we find it?
Right, so we have to go to where our n is 12. X, we're gonna be looking at 4. And P is 0.6. And that should give us this 0.05 number. And that would be if they wanted less than 5, but we want 5 or more, so we need to subtract that from 1. Any other questions? All right, let's talk about part B. If the average number of customers to come into the store in an hour is 20, what is the probability of exactly 6 customers arriving in 30 minutes? And then we'll do it for 10 minutes and 4 minutes as well. So is this a binomial problem or a Poisson?
Poisson.
How do we know that it's Poisson?
Because it has time involved.
Where is the time involved though?
Them arriving.
What was that?
I said them arriving.
Well, our mean is given in terms of time, right? Because so that's why I threw in the word time a bunch in part A, right? We're talking about flights arriving on time 60% of the time. So time doesn't just have to be involved for it to be Poisson. What's the giveaway here is that our mean is 20 customers per hour. So since our mean is given in terms of time, that's the giveaway for it being a Poisson problem.
Could you say that again?
So our mean is given in terms of time, right? So here it's per hour, it could be per day, per year, per minute. And because the mean is given in terms of time, it's Poisson. So we're told that the average number of customers to come into the store is 20 an hour. We want to know the probability of exactly 6 in 30 minutes. So what's our formula for Poisson?
Don't you want to find out how many come per minute first?
Well, before we even adjust our mu, we need to know what other pieces we might need in this formula, right? So what do we need in this formula?
X.
Okay, so we're gonna need to know an x. And what else is in this formula?
E.
So what is E?
Calculator number.
Right, E is just a constant, right? So nothing given to us in this problem is E. E is just somewhere on your calculator, we use that number. So we don't need E. What's X? 6, right? It's the number of customers. So X is going to be 6. Now we can talk about changing up our mean, right? So if it's 20 per hour, and we want to know probability of 6 in exactly 6 in 30 minutes, what do we need to do to that mean? Okay, right, so our mean now is 10 per 30 minutes, right? 10 customers on average show up every 30 minutes. So we could plug it into our formula, right? So mu to the x times e to the negative mu over x factorial. We could do all that. What's another option for us then? If we don't want to plug it into a formula, what did Sam Bloom give you to find these numbers, right? Our tables. So we don't have cumulative Poisson tables, unfortunately. So if that ever comes up on the exam, we can't do that. But we only need individual here, right? Because we want exactly 6. So when we look up in the Poisson table, up along the top are your means, right? So what is our mean for this first part?
10.
It's 10, right? So we look for 10 along the top, and then along the left side should be x's, and our x is 6. So what is the probability of 6 customers in 30 minutes?
0.0631.
Okay. So there's a 6% chance that exactly 6 people will show up in half an hour. So now, the next part of this is exactly 6 customers, so our x stays the same, but now in 10 minutes. So, now would be a good time to come back to this initial mean and find out how many customers per minute. Right, so if 20 customers come in an hour, if we divide that by 60 minutes, we can see that how many customers come in per minute. What do we get?
0.3 repeating.
Right, 0.33. So, if we want to know per 10 minutes, if this is 1 minute, what do we need to do?
Times it by 10.
Multiply it by 10. Okay. But remember, that number goes on forever, right? So our mean, we'll put it in like that. Do you have 3.3 repeating in your table as a mean? Nope. So, what are we going to have to do in this case? If we can't use the table, what do we use? We use the formula. So we look at our formula sheet, right? And our formula here is mu to the x e to the negative mu all over x factorial. So now we start plugging it in, right? 3.333 to the 6th power, because x is still 6, times e to the negative 3.33 all over 6 factorial. Right, so then we just plug in each part that we've already written down. I would recommend doing this in separate steps in a calculator, right? I would first do your mu to the x, find out what that number is. Then do e to the negative mu, find that number, and then do 6 factorial and find that number. And then do the math involved.
I got 0.0680, you round up.
Okay, 0.0680. So there's a better chance of exactly 6 customers showing up in 10 minutes than there is in half an hour. Now, for this first part, when we found this 0.0631, she does expect you to use the table when you can. However, I would still write all of that out. Show her that you know the formula. Show her that you know how to input the information into the formula. Then just look for the answer in the table. Because that will get you points. So you'll want to write out your formulas. You'll also want to write out that sort of information, right? Everything that's given to you. The mean, your x, over in binomial problems, your p, right? We want to write those out because that will help you get those extra points. So now, this final part, the probability of exactly 6 customers in 4 minutes, what's going to change here? Your mean, right? So if it was 0.33 customers per minute, what's our mean now for 4 minutes? We're getting 1.33, right? Per 4 minutes. So we once again input all of that into our formula. So 1.33 to the 6th power, that's still our x, times e to the negative mu, all over 6 factorial. So another reason to do this all separately is we should already know what 6 factorial is, right? So we could just plug that number into the denominator instead of having to go through your calculator to figure that one out again. So when you do all of that, what do we get as our probability? Point 0.0021. Right, so that's 0.2% chance of happening. So 6 people coming in 4 minutes probably isn't going to happen. So how do you guys feel about Poisson problems? And deciphering when to use binomial versus when to use Poisson. Right, are we good there? Any questions over number 2? Okay. So, let's take a look at number 3. So it tells us that the average sales for our company is $300,000 with a standard deviation of 25,000. What do your sales need to be in order to be in the top 9%? Right, so this is the more likely situation out in the real world. Right, a lot of the homework and stuff in class might have been, you know, here's your sales, what percentile are they in? Out in real world scenarios, we want to be top 10%, top 5%. And we find out this is what we need to hit in order to get there. So, how can we figure out top 9%?
You have to find the z-score.
We have to find the z-score, right? So, if we draw a bell curve, where's the top 9% going to be? Over at the right tail, right? So, over here, what's the area to the right? 9%, right? So that's 0.09. So the area to the left would be what? 0.91. So how do we find that z-score?
We looked up 0.91.
Right, we're looking up 0.91 inside the table, inside your z table. So we're looking for an area that is 0.91. What are you guys finding?
1.34.
What was it?
1.24.
1.34, right? So that's, that area is what, 0.9099, right? So that's just the closest one that we're going to find here. So our z-score is 1.34. We want to know what our sales need to be in that top 9% though. So now what do we do?
We times that by the standard deviation.
Okay. So let's just take a look at our z-score formula, right? Yeah. So our z-score is 1.34. What's our mean? 300,000. What's our standard deviation? 25,000. So we're looking for X, right? So now what do we do?
Multiply both sides.
Right, so we go 1.34 times 25,000 gets us that. Why does this make sense? This 1.34 times 25,000.
That's how far it is from the standard deviation from mean.
Right. All a z-score is how many standard deviations we are away, right? So we are 1.34 standard deviations away from the mean. So when we multiply this out, it tells us the exact amount away from the mean that we are. So when we multiply that out, what do we get?
$32,500.
Okay. So your sales need to be how much? Right, we just add. We need to be this far above our mean in order to be in the top 9%. So it's important to be comfortable with this formula, our z-score formula. So in that way, you're not only using it to find your z-scores, but you can use it to find any piece of information there. So any questions there in number 3? All right. So, if we look at number 4, it says the average price of a new car is $33,000, and the population standard deviation is $3,500. 500 people bought new cars in Arizona last week. What's the probability that a random sample of 45 car buyers in Arizona last week spent within $1,000 of the average price? So what are the steps that we need to do?
Write the information you know.
Okay? So what information do we know for sure in this problem?
So sigma is 3,500.
Okay? What is 500?
The people were X, isn't it? Because the people bought the new cars.
It's not gonna be